Okay, in this problem we're working with Chebyshev's theorem. From a sample of many compact cars, the average gasoline mileage is found to be approximately 20 miles per gallon. So I'll say mu is 20 miles per gallon for the average, and the standard deviation is 4.5 miles per gallon. Find the z-scores for the values in the following, and then use the formula given by Chebyshev's theorem to answer the questions. So part A, what can you say about the percentage of many compact cars that will get between 11 and 29 miles per gallon? I'm going to go ahead and calculate the z-scores for that. The z-score for 11 is -2, so I'm 2 standard deviations to the left of the 20, and the z-score for 29 is +2, so I'm 2 standard deviations to the right. So when I say the percentage of many compact cars that get between 11 and 29 miles per gallon, I'm basically saying the percentage of many compact cars that are within 2 standard deviations of the mean. Chebyshev's gives us a formula to calculate a percentage by taking that number of standard deviations. 1 minus 1 over, in this case, 2 squared will give us 1 subtract 1/4 is 3/4, which is 0.75. And then Chebyshev says take that percentage, and the answer is at least 75%. So at least 75% of the many compact cars will be within 2 standard deviations of the mean. In this case, at least 75% of the many compact cars will get gasoline mileage somewhere between 11 miles per gallon and 29 miles per gallon. Now, key words here for Chebyshev's is at least. At least 75% is not necessarily 75%. It's 75% or more. It could be much higher. As a matter of fact, if you look at the empirical rule, if we happen to know that this was a mound-shaped distribution, we could do a better job of approximating what percentage it would be. It would be approximately 95%. Approximately 95% of the values in a data set will be within 2 standard deviations of the mean. But that's only if it's mound-shaped. Empirical rule only applies to mound-shaped distributions. In this case, we're not told it's mound-shaped. We don't know if it's mound-shaped. Chebyshev's theorem applies to any data set. It doesn't have to be mound-shaped. But notice the two answers here. If I didn't know what the distribution was, I would use Chebyshev's theorem, and it would tell me that at least 75% of the data values will be within 2 standard deviations. Suppose later I found that it was a mound-shaped distribution. Then I could better approximate that by saying 95%. But there's no contradiction. At least 75% does not contradict approximately 95%. At least 75% is 75% or more. It could be 95%. And if it's a mound-shaped distribution, it is approximately 95%. But Chebyshev's guarantees that in any data set, regardless of whether it's mound-shaped, that at least 75% of the values will be within 2 standard deviations. Let's go on and try part B. I'll calculate the z-scores here also for 6.5 and 33.5. In this case, the 6.5 is 3 standard deviations to the left, and 33.5 is 3 standard deviations to the right. Using the formula, I'm talking about within 3 standard deviations, so I'm going to plug that in. And I get 1 minus 1/9, or 8/9, and 8/9 is 0.88, we'll say approximately 89%. So the answer then is at least 89%. So the percentage of many compact cars that will get between 6.5 miles per gallon and 33.5 miles per gallon is at least 89%. At least 89% of the data values in a data set, any data set, will be within 3 standard deviations to the mean. If it happened that we also knew that it was a mound-shaped distribution, we could go ahead and apply the empirical rule and say that almost all many compact cars would get between 6.5 and 33.5 miles per gallon. But not knowing that, we'll say it's at least 89%. Part C. What can you say about the percentage of many compact cars that will get between 14.37 and 25.63? Calculating the z-scores. The z-value for 14.37 is negative 1.25, so it's 1 1/4 standard deviations to the left of the 20, and the 25.63 is 1 1/4 to the right. So Chebyshevs, you can put in values other than 1, 2, and 3 standard deviations. So if I put 1.25 in there and square it, I get approximately 0.36. So the answer is at least 36%. At least 36% of the mini compact cars will get somewhere between 14.37 miles per gallon and 25.63. At least 36. 36 or more, but at least 36. What would the empirical rule say about that? Well, unfortunately, the empirical rule only tells us about 1, 2, and 3 standard deviations. So really, we couldn't apply the empirical rule here, even if we did know that it was mound-shaped. Now, part D, what can you say about the percentage of mini compact cars that will get between 15.5 and 24.5? Well, you'll notice that the z-score for the 15.5 is -1, and the z-score for 24.1 or 0.5 is 1. So what does Chebyshev say within 1 standard deviation? Well, that would be 0. So at least 0% of the mini compact cars would get somewhere between 15.5 and 24.5 miles per gallon, or within 1 standard deviation of the mean. Chebyshevs would say at least 0%. Well, if we happen to know the distribution is mound-shaped, we could say that it's approximately 68%. So, again, no contradiction. At least 0%. At least 0% is 0% or greater. And in a data set, if you don't know it's mound-shaped, you can guarantee there's at least 0% within 1. If you know it's mound-shaped, then it's approximately 68. Again, the key words here between Chebyshevs and empirical rule. Chebyshevs is giving you a percentage in which you can make a statement. At least that percentage is within a certain number of standard deviations. Empirical rule is giving you an approximate value. Approximately 68% means close to 68%. Right? At least 95% means close to 95%. At least 75% means 75% or greater. So there's quite a difference between it. And when you answer a question with Chebyshev's theorem, make sure you use the words at least. And empirical rule, keep in mind that those are approximate percentages. So these two theorems work together, and they don't contradict one another. Chebyshev's is true for any data set. And empirical rule is true only if you know that the distribution or the data set would give you a mound-shaped histogram. Hope this helps.